let me introduce to you our very first speaker, Brian Shoichet. After his undergraduate work in chemistry at MIT, Brian earned his PhD here at UCSF in pharmaceutical chemistry in the lab of Tack Kuntz. He went on to be a Damon Runyon Cancer Research Fellow at the Institute of Molecular Biology before starting his own lab at Northwestern University School of Medicine. He returned to UCSF in 2003, where he is now a professor in the Department of Pharmaceutical Chemistry. The title of his talk is A Metabolic Code for Drug Discovery. Brian.
All right, thanks Liz and Dan and all, and thanks for coming. It's great to follow. It's always daunting to follow Nobel laureates. But it's great to follow them in a sense because they introduced one of the key themes that's made UCSF what it is, and that was the real scientific founding of UCSF happened at the time when the molecular biology revolution was just getting underway. And because it was, I think Mike Bishop said it was, or maybe it was Holly Smith, said it was we were sort of a tabula rasa for creating the faculty. The faculty that were, going to be the ones who created the molecular biology revolution were being recruited here at that time. So that was terrific for the institution, and we've ridden that wave ever since. In my own field, in pharmacology and in drug discovery, the very premise of molecular biology wasn't adopted until very late. And in molecular biology, one of the ways of summarizing one of the themes in molecular biology is that one gene, one protein, right? That was one of the original revolutionary ideas. And in pharmacology, the way we've taught it, and drug discovery, the way we've taught it for the last 30 years is one gene, one protein, one drug. But pharmacology in its foundational years, and in the years when many of the drugs that we still use were discovered, went exactly the opposite way. So instead of going from a target, a protein, to discover drugs, what people did was they started with collections of drugs and put them on whole animals or whole tissues and tried to infer targets that they thought existed, but they never cloned and they never purified. So it was completely opposite. And so this gentleman, Raymond Ahlquist, for instance, started with a collection of molecules that would turn on the adrenaline response, and based on different patterns they had on different whole tissues, inferred that there must be two receptors, adrenaline receptors, which he called the alpha and the beta adrenergic receptors. And based on that paper, which came out in 1948, this gentleman, Jim Black, thought that he could get molecules that would be specific for the beta adrenergic receptor, and that led to this molecule, which is propranolol, which was the first beta blocker, and that became a franchise in drug discovery. And based on that molecule and other work, other investigators came up with molecules that were specific for what they called the beta-1 adrenergic receptor, and the beta-2 adrenergic, atenolol was the example shown here for the beta-1. It was one of the first specific beta blockers, and albuterol for the beta-2 adrenergic. That's what you take for people who have asthma to relax the bronchioles. And there's this idea that there was a beta receptor and a beta-1 subtype and a beta-2 subtype was all based on this idea that you would put collections of small molecules on whole tissues, and you would infer the existence of this beta-2, this mythical beta-2 receptor. And this idea held right up until the mid-1980s in pharmacology. At UCSF, by the early 70s, people were working on the molecular view, so this is the Crickian view of information flow, the central dogma of molecular biology. And where it hit pharmacology was when these two gentlemen, Brian Kabilka, my friend and colleague Brian Kabilka, and Bob Lefkowitz cloned this molecule, the beta-2 adrenergic receptor, this mythical molecule, the beta-2 adrenergic, and showed it was a real thing that you could clone and purify, and subsequently Kabilka solved the structure of it. And for that, and for their earlier contributions, he and Lefkowitz were given the Nobel Prize in Chemistry 3 years ago. And that has taken over. So from that point, pharmacology became a molecular biology field. The thing about the classic period of this funny idea of going from ligands to targets was very successful. They discovered a lot of drugs, and the drugs they discovered, almost by necessity, had these virtues that we have sort of given up in the molecular field. They were all permeable. They were all penetrant. They got into the tissues. And then they had these activities that acted on whole tissues. If they didn't have those features, they wouldn't have been discovered in the first place. And we no longer have it. When we go from a protein-based view of drug discovery, we no longer have those things. And so what we've been doing in our lab is go back to this very odd, but in its own way very successful view of molecular biology, and of drug activity, and say, let's classify proteins not by their sequence or their structure, which is how I was trained, and a lot of what we still do, but based on the small molecules that bind to them. And so let's recreate the social networks for what proteins are similar to what other proteins by the small molecules they bind. And when you do that, you get this vast reorganization of the protein similarity networks. Molecules that have nothing to do with each other, proteins that have nothing to do with each other from sequence or structure or our classic ideas of function, come together as similar because they bind similar molecules. So ion channels start looking like GPCRs, and GPCRs start looking like nuclear hormone receptors. Of course, they don't look like each other in 3 dimensions, but they do bind very similar small molecules. And from that idea, we started to have this great time saying, well, look, if these 2 targets, which supposedly are very different from one another, bind similar, not the same, but similar ligands, we think we should be able to say that such-and-so drug for this target will bind to this target. And that's what, for the first 5 years of this research program, up until very recently, that's all we did. We would say, oh, well, we predict that such-and-so transporter looks at such-and-so receptor. So like the serotonin transporter looks like the beta-1, the beta blocker receptor. And sure enough, we could predict and test that Prozac, this SSRI, this sort of specific serotonin reuptake inhibitor, would hit the beta-1. And that was consistent, it turns out, with a lot of its side effects, postural hypotension and some other things. Tropicitrin, which is developed for the serotonin ion channel, turned out to act very well on the serotonin GPCRs, which have nothing to do with each other except they both bind serotonin. I was talking to Lauren about Benadryl. Benadryl, which many of you take, it's the PM medicines that you take if you've got a cold. Sometimes you take it for sleep. Well, it's a very old drug. It comes out of the classic period of drug discovery, and it has all these funny off-target effects. And one of them is agitation, and that turns what we could predict and then show experimentally was that Benadryl would hit the dopamine transporter and keep dopamine and other signaling molecules in the synapse longer and lead to this agitation side effect. And so this went on, and we had a great run, and we're still having it, predicting all these funny off-target effects for drugs. But eventually, over time, we started to think, but look, it's not like molecular biology was wrong, right? Why should these things work? Why should we have this funny success with the ability to predict that these very unrelated targets, apparently unrelated targets, should bind similar small molecules? And what we've come to realize in the last year and a half is that this baffling and profound promiscuity of small molecule drugs, for which my field, medicinal chemistry and pharmacology, have long been lashing ourselves as why can't we get more specific drugs, right? It mimics the promiscuity of endogenous hormones and neurotransmitters. It turns out that the neurotransmitters, the neurotransmitters that are hopefully not putting you to sleep right now but are keeping you a little bit awake, do the same thing. So serotonin hits serotonin receptors, but the serotonin receptors can look very different. So there's an ion channel serotonin receptor, and there's a lot of G protein coupled, just a different G protein coupled receptor, serotonin receptors. They don't look similar at a molecular level, but their mission in your cells and in your tissues is to bind serotonin, and they do it at different time scales. The ion channels have a very fast response in the millisecond time domain. The GPCRs are slower. Same with ATP. ATP is not only an energy molecule, it's a signaling molecule, but it binds ion channels and these G protein coupled receptors. Acetylcholine hits, same thing, ion channels and GPCRs. Estrogen hits, of course, the estrogen receptor, but it also, I'm getting a time signal. It also hits a G protein coupled receptor. Okay, I won't go on. So why does this happen? There's two fundamental reasons. One is we don't have very many neurotransmitters and hormones, and they don't evolve. Once you've got serotonin, you're stuck with serotonin, because serotonin is not coded. Unlike the proteins that respond to serotonin, which are part of the genetic code, they're proteins, serotonin is a small molecule, and it basically doesn't evolve. It's frozen in time and has been for basically 3 billion years. And the second reason is that the cells, meanwhile, have responsibilities in multiple time domains. They have to respond in the millisecond time domain and the second time. So they repurpose this molecule. And so what's all that got to do with the price of cheese? Is that when we can't, it's not a bug of pharmacology that we have promiscuous drugs. It's a feature. They're mimicking the patterns that are ingrained in evolutionary history of signaling molecules acting through these very different proteins. So I would say, UCSF has been built on the molecular biology revolution and on, the genetic code and its continued ramifications. But underlying it is this metabolic code against which the proteins have evolved and repurposed. And there's no getting away from it. But the good thing is that once you've had that aperçu, you can use it to get molecules with greater efficacy because they exploit the same pathways that our endogenous neurotransmitters and hormones do. Thank you very much.